Turns out that the three groups of stars, main sequence, red giants, and white dwarfs, differ from each other tremendously in terms of their average density. What do we mean by a density of an object? It's mass per unit volume. That's what we call the density. Okay, so the average density is basically the mass of the star over its volume. And once you know the radius of a star, you can calculate its volume because it has a spherical shape. Once you know the radius of a sphere, you can calculate its volume. So when you do that for the three groups of stars, then you end up with the following numbers. For main sequence, you end up with a value of about 1 gram per centimeter cubed. This is roughly the density of water under normal conditions, right? The water density under, at, say, a room temperature and atmospheric pressure is exactly 1 gram per centimeter cubed. So that is the average density of a main sequence star. Red giants have much lower densities. Their average density is about 10 to the minus 6, 1/1,000,000th of this value, gram per centimeter cubed. And white dwarfs are extremely dense. The average density is about 5 times 10 to the 5 grams per centimeter cubed, right? So it is like 500 kilograms per centimeter cubed, half a metric ton of material packed into a cube 1 centimeter on the side. It's like taking a smart car and compressing it into a little cube, which is 1 centimeter on the edge. So you see that they are extremely dense compared to main sequence stars, and of course compared to the red giants. Well, this difference in density has an important consequence on the line widths of their spectra. Turns out that the gas emitting light and the gases at low density, then the spectral lines are very sharp. As you increase the density, the collision between the atoms of the gas induces the broadening of the spectral lines. So schematically, these would be the spectral lines of a low density gas. They are sharp, that is well defined. But now if I would take that same gas and compress it and keep the temperature the same so that it emits the light, then what happens is that these sharp spectral lines get broadened into the bands. I'm exaggerating, of course, but just to make the point. Right? In the low density gas, the atoms do not collide that frequently. It's just like going to a mall at the middle of the summer where everybody's on vacation, right? The odds of running into another person are pretty low. But if you go to the mall just before Christmas, everybody's bumping into each other, right? The density is high. People are interacting. So it's the same with the gas of low and high density, and these collisions turn out to broaden the spectral lines.